I'm Mrinal. I work at Tata Institute of Fundamental Research. I'll generally be doing the second half of the coding theory lectures for the next 4 days. Many thanks to Prahladh, Venkat, and Irit for inviting me. Thanks for being here. Before I start, I see that there are people in the audience who have taken some version of a coding theory class with me. Now you know where the magic trick came from. So our plan for this lecture is the following. We are going to see an algorithm for efficiently decoding Reed-Solomon codes from half the minimum distance. And then we'll define this notion of local decoding that Swastik mentioned but couldn't define towards the end of the last lecture. And then we'll define what are called Reed-Muller codes. And then we'll see a local decoding algorithm for Reed-Muller codes. And hopefully we'll do all of this in the next 60 minutes. So if you have questions in between, please ask. Raise your hands and ask, or just ask. I can't see hands at the end of the room at this point. So Reed-Solomon codes were defined in the 50s. Let's recall what the definition was. So we had a finite field FQ, and Q was equal to N. And the code itself was defined as the set of, and let's say that FQ, we labeled the elements of the field as alpha 1 up to alpha n. And the code words corresponded to evaluations of low degree polynomials at these points. Let's say it's at most k. So the distance of the code, so the minimum distance of the code, delta, was n minus k. And we can hope to decode these codes from up to half their minimum distance at this point, which is, we'll try to decode them provided the number of errors is less than n minus k over 2. So for this discussion, we'll be in the setting where the number of errors is strictly less than n minus k. Okay, so these codes were defined in the 50s, and we have known efficient decoders for these codes since the early 60s, and there are various different kinds of decoders. There are algorithms of Peterson, Berkeley and Macy, Sugiyama, but the decoder that we are going to see is from the late 80s. It's called the Berkeley-Welch decoder. And this is going to be an efficient algorithm that given us that will take as input a received word. So we'll be given a string of length n over fq to the n that will be close to a legitimate code word of this code, close in Hamming distance, where the number of errors will be less than n minus k over 2, and our goal will be to find the closest code word. So let's set it up. So our input, so received word, so it's I'm going to, so let's think of this as R, which is beta 1 up to beta n, such that there exists a C in the code, say RS n comma k, such that the Hamming distance of R from C is less than n minus k by 2. And our output will be to find the C. And C is going to correspond to evaluations of some univariate polynomial P. So let's say we'll try to find P. Okay. So now let's, for starters, let's pretend that there were no errors. If there were no errors, then what is this problem? We are given evaluations of a degree k polynomial on n inputs, no errors. So you know all the evaluations correctly. And how do we find the polynomial in that case? we will interpolate, right? In that case, this is our standard interpolation problem. But in the setting that we are in, we will not be, the evaluations are not going to be correct. There will be a bunch of errors in this. So what we are doing is some kind of a noisy univariate polynomial interpolation. So this is a and noisy meaning that some of the evaluations are not correct. There are errors. All right. So Berkeley-Welch has it's often taught in coding theory classes, at least in computer science. But I'm going to do a version of it, a slight change in exposition that will make it easier for us when we talk about decoding beyond half the minimum distance. And this slight change in exposition annoys Jayakumar. So there's an added advantage here. Okay, so we'll stick to that. All right, so what's the idea? So maybe the initial thing to think about is that the received word sort of specifies a bunch of points in 2 dimensions for us. Right? So we know this the coordinate beta I is supposed to be the evaluation of P on alpha I. So we can, given this received word, we can try to plot these points in the plane. How are we plotting finite fields? That's a different issue, but you could think of points alpha 1, beta 1, alpha 2, beta 2, alpha 3, beta 3, and so on. And somewhere here, there's an alpha and beta. And our goal is to find a low degree polynomial such that its graph passes through many of these points. Right? That's the problem. Okay, so let's again pretend that there were no errors. So if there were no errors, we know that we can do interpolation. But but what does it say about these points in 2-dimensional space? So it says something interesting, and a generalization of that observation sort of will take us towards the algorithm. So if there were no errors, so no errors. So in this case, if we look at the polynomial q of xy, it's a bivariate polynomial. It's just y minus p of x. If we take the polynomial y minus p of x, this polynomial vanishes on all of these points. Right? So let's call this q naught. Q naught of alpha I comma beta I is 0 for all I. Is that okay? So if there were no errors and we plot this guy, it's going to pass through all of these points exactly. Now suppose there are a few errors. So some of the points are incorrect. So there's an error here, maybe there's an error in alpha 7 comma beta 7. Maybe alpha 17 comma beta 17, and so on. So some points are erroneous. I want to claim that this sort of a statement is still true. There is a low degree bivariate polynomial that vanishes on all of these points. Sorry, is there echo or? Then now it's okay. I can hear an echo. Okay. So good. So now we have a subset of these points where there is some error. And I want to claim that qualitatively, this kind of a statement is still true. There is still a low degree q of xy that will vanish on all of these points. Do you see what it is? Suppose there's exactly one error. Suppose there's exactly one error. It's at this point. I would say that there is a low degree bivariate that vanishes on all of these points. Great, excellent. So q1 of xy. So the suggestion is let's look at q0 of xy and multiply it by maybe something like x minus alpha 70. For all the points where there is no error, q0 is going to vanish. But when we plug in x equals alpha 17 in Q naught, maybe this is non-zero because there was an error here. But in that case, this factor will vanish and this polynomial will vanish everywhere. Is that good? All right. So one observation that we can make from this is that, oh, by the way, how does this generalize? What about the case when there are many points where there is an error? How do we generalize this? Right, so we can write Q naught of xy, and we can multiply it by all the points, all indices I, such that I is an error. And we can write x minus alpha. This is one example of a polynomial that vanishes on all the points, all these points in the two-dimensional space, even now. Very good? Great. So, okay, so what's the takeaway from this? So one takeaway from this is that I mean, there are various things I have to make formal, but I keep saying a low degree bivariate. I haven't told you what the degree bounds are. But morally, what's happening is that there is a low degree bivariate that seems to vanish at all of these points. Okay, and note that because of the way these guys are defined, the polynomial p of x is hidden somewhere in these qi's. Right? If I'm given q naught, I know exactly what p of x is. But even if I'm given q2, I sort of know what p of x is. If somebody gave me q2, we can figure out what p of x is. How do we find what p of x is? So let's write this. So q2 is, let me call this, let me give this a name, call it e of x. So q2 is y minus p of x times e of x, which is y times e of x minus p of x times e of x. So if I'm given q2, how do we get our hands on p? If I'm given q2, I know what's the coefficient of y in q2, and I know what's the y free term in q2. And I can divide the y free term by the coefficient of y, switch some signs, and get my hands on p. Right? So if q2 was of the form y times some a of x plus b of x, then in this example, p of x is equal to negative of b over a. Good, but all of that is happening for a specific choice of q that we took. You could think of 100 other polynomials that will have the same properties. It will vanish on all of these points in the 2D space. It's unclear whether any of those polynomials have anything to do with the polynomial p that we are interested in. So there is that humongous caveat with what we are talking about. But for this specific choice of QIs, is this clear? Is it sort of clear what we are doing? Questions? Okay. All right. So sort of the main, so one insight in many of these algorithms for decoding Reed-Solomon codes. So here we are talking about the case where the number of errors is less than half the minimum distance. But in 2 lectures from now, we'll talk about decoding Reed-Solomon codes where the number of errors is much, much larger. And one insight in all of those algorithms is that, and this is not obvious at all. So let me write it. So any low degree non-zero q of xy that vanishes on the points alpha I, beta I, as I ranges from 1 to n, contains in its belly information about close enough code words. And this is one part of it. The other part is, moreover, all these code words can be recovered efficiently. So it's a surprisingly strong generalization of the toy observations we were making. Our observation was that here was that if the points given to us are close to the encoding of are close to a legitimate Reed-Solomon code word, then there exist interesting bivariate polynomials that vanish on all of these points. And from those bivariate polynomials, we are somehow able to get our hands on the P that we are interested in. But this is an observation about a specific bivariates that we designed here. One of the key high-level takeaways of Berkeley-Welch's algorithm that we are going to see now, and we'll talk about Sudan's algorithm and Guruswami-Sudan's algorithm that will decode Reed-Solomon code from far beyond the n minus k over 2 bound that we are looking for. The insight is that any low degree non-zero q of xy that vanishes on the given data contains in its belly some information about close enough code words. Moreover, we can use this Q to recover these code words efficiently. It's a very non-trivial statement. It's at least to me, it's not obvious why this ought to be true when the parameters are interesting. All right. Okay. So with that outline in mind, let me describe the algorithm. The algorithm really just has two steps. The first step is the interpolation step. And this step is going to be like this. We'll try to get our hands on some low degree q of xy of a nice and special form that vanishes everywhere on the given data. So find a non-zero q of xy of the form of q of xy is going to look like some y times a of x plus b of x. And it satisfies a few properties. So such that the first property is that for all I, q of alpha I beta I is 0. The second property, so I've been saying we should look for q of low degree. The degree of q is low. Based on just the form of q, we know that the degree of q is low in y. The y degree is 1. We have to impose bounds on the degree of a and b. Let me impose the bounds and we'll come back and see why these make sense. So degree of y and degree of a is let's say less than or equal to n minus k over 2, and degree of b is at most n plus k over. Okay, so that's what I mean by low degree q in the current context. We are going to find a q of this form that vanishes on all the given on the 2D points that we have plotted from the received word, and the degree of a is something, the degree of b is at most something. Yes. Yeah. What should be the second step based on, the first step is like what we were doing here. What should the second step be? Right, we should really try to output minus b over a. But we'll output this, but up to some checks and balances. See, given when we are given the received word, we are not, oh, I see, the way I've stated the problem, we have a promise. Okay. So, let's say output negative of b over a. Yeah. Yeah. It is a polynomial. A divides b. Look at the examples here. This was a, this was b. So a divides b. We will have to argue that this is the case there. Yeah. So it may not even be a polynomial. From the expression, that's what it looks like, but it will be a polynomial. Okay. Questions about the description of the algorithm? I mean, I haven't said how we are going to do step one. How do we get our hands on a non-zero Q with these properties that satisfies the conditions that we want? Yeah. No. Right. I mean, the version of the question we asked here was a promise problem. We are given a received word with the promise that there is a C that is close to the received word. For this case, it will be true that A divides B. We will argue, but in general, this may not be true. I mean, we may be given a received word with no guarantees on whether there is a close enough code word or not, and you can ask something stronger. You could say, well, if there is a close enough code word, output it, or say that, well, there is nothing close enough. So in that case, we can't. So the second step has to just do some sanity checks. Questions? No, yeah, it's okay. Yeah, we'll see. I'll say something about it, but I want to stick to what's there for now. Questions? Other questions? Are we good? All right. So, I mean, the first thing to do is to describe how do we do the interpolation step. And when we were doing it for these toy cases, we were sort of just looking at the data by explicitly and coming up with something. But how do we do this? I mean, here we assume that we know where the errors are when we were constructing this polynomial, but generally we will not be aware where the errors are. So, so this is it's a nice trick to know. So our goal is to find Q of xy of this form which satisfies these conditions. Finding Q of xy is the same as finding the coefficients of A and B. Okay, so let's write A of x as A naught plus A1x plus A2x squared, so on. And its degree can be as large as n minus k over 2. So it's A n minus k over 2 times x to the n minus k over 2. Okay, yeah, I mean, if 2 doesn't divide this, one has to worry about other things, but I'm not going to be worrying about it. Okay, so A is some polynomial of this form. B is some polynomial of the form b naught plus b1x plus b2x squared, so on, up to b n plus k by 2 times x to the n plus k. Finding Q is the same as finding A and B, and finding A and B is the same as finding these coefficients. If we can figure out the little ai's and the little bi's, we are done. We have found a Q. But we know that because of the degree constraints, we know that A and B have to be of this form. Okay, so we will think of A and B as polynomials in this form. We will think of little ai's and little bi's as formal variables. These are variables whose value we want to find. Let's try to understand what does this condition look like. What does it mean to say that Q of alpha I beta I should be 0? So Q of alpha I beta I should be 0. This is the same as, and this is equivalent to A of alpha I times beta I plus B of beta I should be 0. Right, but what is A of alpha I? A of alpha I is sum over j, A sub j, alpha I to the j times beta I plus sum over j, B of j times beta I to the j. This is what we are asking for. But this is a linear, so the knowns here are alphas, betas. Alphas, betas are known to us. Sorry. Is that okay? Yeah. Sorry. All right. So this condition is the same as this condition, but in this constraint, notice that alphas and betas are known to us. The things that are unknown to us are little a's and little b's. But this is a linear constraint in little a's and little b. It's a homogeneous linear constraint in little a and little b. So in particular, these for all I in n, q of alpha I beta I equals 0, it's a collection of homogeneous linear constraints in little ai's and little bi's. So it's a linear system. So the question of getting our hands on little ai's, little bi's satisfying this condition is the same as solving a linear system. So the way we will do this is, I mean, this is just a linear system solver. That's how step 1 is implemented. Okay. The question of interest should be, why does this homogeneous linear system have a non-zero solution? And we can construct the linear system, we can solve it, but what guarantees that there must be a non-zero solution? When can we guarantee that a homogeneous linear system has a non-zero solution? If the system has more variables than constraints, then the solution space is in a fine space of dimension at least 1. So there must be at least one non-zero solution. So if we can somehow stare at this linear system and say that, oh, the number of constraints is smaller than the number of variables, strictly smaller than the number of variables, then we are good. Then the system will have a non-zero solution. How do we solve a linear system? Gaussian elimination, yeah, something. So Gaussian elimination. So we use our favorite linear system solver to get our hands on a non-zero solution. So let's compare the number of variables and the number of constraints. How many constraints are there? How many constraints are we imposing? N. How many variables? How many variables are there? So A has degree n minus k over 2, so it has n minus k over 2 plus 1 variables. And B has degree n plus k over 2, so this is n plus k over 2 plus 1 variable. So that's n plus 2 variables. It's clearly more than n. So the system will always have a non-zero solution. We will get our hands on that solution and an output minus b over a. Okay, so the algorithm is clearly polynomial time, right? All we are doing is solving a linear system, getting our hands on a solution, and then doing some polynomial division. What we need to argue is that this will output the close enough code word that we want it to output. So all we need to do to prove the correctness is to prove the following lemma. Let this be the be such that the Hamming distance of R from I'll write Hamming distance of R from P, but what I mean is look at the encoding of P, look at the vector of evaluations. This is n minus k over 2. Then P equals minus b over a. I should say more. Let Q of xy be any non-zero polynomial from the interpolation step. Once we prove this, we are done. That proves the correctness of the algorithm. Okay. Why is this true? Which part is not visible? This line is not visible. Okay. Let me say what I meant, and yeah, I'll write bigger. So this says let Q of xy be any non-zero polynomial that we got from the interpolation step of the algorithm. And what we want to show is that if P is the polynomial that's close to the received word R, as was promised in the problem, then P is equal to minus B over A, where B and A are from the definition of Q. Okay, so here's one way of looking at this. So I want to look at the polynomial R of X, which is Q of X comma P of X. So I'm going to replace the variable Y by P of X. And what is this? So this is equal to A of X times P of X plus B of X. So it's some univariate polynomial. What is the degree of this univariate polynomial? How large can the degree be? So the degree of this can be the max of the degree that comes from B and the degree that comes from the first part. The degree that comes from B is n plus k over 2. The degree that comes from the first part will depend on the degree of A and the degree of P. The degree of A was at most n minus k over 2. The degree of P was at most k. So both the parts are really giving you a bound of n plus k over 2. So the degree of R is at most n plus k over 2. Okay. So R is a univariate polynomial of degree at most n plus k over 2. Okay. So here's the key observation. If P of alpha I equals beta I, then R of alpha I is 0. Yeah. We said, no? I mean, the finding Q is every constraint here is like writing a homogeneous linear constraint. So we are going to construct the linear system corresponding to the n homogeneous linear constraints, solve the system using your favorite linear system solver, find a non-zero solution in the from that. So that's how we find Q. Yeah, I didn't say it in the algorithm, but I said it after. Okay. So the claim is that if alpha I is a good point, if meaning P of alpha I equals beta I, there's no error here, then R of alpha I must be 0. Why is this true? So what is R of alpha I? So R of alpha I is Q of alpha I comma what? Comma P of alpha I, but P of alpha I is equal to beta I. So this is equal to Q of alpha I comma beta I. But Q of alpha I comma beta is 0 because that's how we found Q. It was one of the constraints we imposed on Q. So this is 0. So if P of alpha I is equal to beta I, then R of alpha I is actually 0. Which means that at every point where P agrees with the received word, at every point where there is no error, R of alpha I has a root. Okay. So at every point of agreement between P and R, P and little r, the received word, R of X has a root. But suppose P and R agree at more than n plus k over 2 points. So if number of agreements is strictly greater than n plus k over 2, then what can we conclude? R is a polynomial of degree at most n plus k over 2, but it has more than n plus k over 2 roots. What does that mean? It means R is 0. So if the number of agreements is greater than this implies that R of X must be 0, which means that A times P plus B must be 0, which means that P must be equal to minus B over. All right. Okay. Questions? What did we do? We we took our q of x comma y and we plugged in y equals p of x. That was always the plan, right? If you look at the toy examples. And then we argued that when we plug in p of x in place of y, the univariate polynomial we get is identically 0, assuming that p has sufficiently large agreement with the received word. If it's identically 0, then p equals minus b over. So that completes the proof of correctness. There's one tiny catch here. Actually, there are two tiny catches here. Okay. So one catch is that I promised more. I mean, here we are only proving the correctness of this if the number of agreements is more than n plus k over 2, strictly greater than n plus k over 2. We promised more. I mean, we should have really worked when the number of agreements is greater than or equal to n plus k over 2. So that's one part of it. The other is q is non-zero, and we are dividing by a. So we should have convinced ourselves at some point that if q is non-zero, then a is non-zero. So this is a legit operation. Both those things are true. If you stare carefully, you will be able to get it to work for this, and it's proving this. And you can also stare at q carefully and notice that if q is non-zero, then a must be non-zero. I am not going to do that. Questions? All right. If not, we'll move on to other things. We are slow. Yeah, it does. Yeah, it means that. Okay. All right. I mean, one of the takeaways should be the sketch of the algorithm. This is a sketch that we are going to be using again and again in 2 lectures from now. The other thing is that it's a very simple algorithm to write, very elementary. But I think this shouldn't fool us into thinking that it's an easy algorithm. I don't think it's easy. It's one of the cleverest algorithms of all time. So yeah, good. So yeah, you can be careful about it, and you can get n plus k over 2. There is some slack there. Other questions? Okay. Okay, good. So then let's move on to other things. While I'm raising the board, you can ask questions if you have. Yeah, you wouldn't have enough. Yeah, yeah, yeah. Just so happens that we know there is a exactly. So we can use the fact that there is a solution to argue. Yeah. Okay, so let's change topics a little bit and talk about locally decodable codes. And so the high level idea here is the following. So in the previous lectures, Swastik defined the notion of decoding and encoding, etc. And we saw a decoder in action. We took an interesting code and designed an efficient algorithm that decodes it from half the minimum distance. The setting of local decoding is the following. So again, we are going to be given a received word. And this time, I'm not interested in finding the closest code word. I don't want all of it. All I want is a particular coordinate of the code word, an arbitrary coordinate of the code word. So I want, so suppose this is the received word, and suppose the closest code word was C. And R and C disagree on a few places, maybe here. And our goal is to find the ith coordinate of C. I don't want all of C. We are happy to settle with the ith coordinate of C. This is a natural problem that shows up in a variety of settings in complexity theory, pseudo-randomness, etc., etc. But for now, just let's believe that this is an interesting problem to consider. We'll see an interesting algorithm for doing it, and I think that should convince you that it's interesting. So the question is, I'm given R and I'm given an index I, and the goal is to find C sub I. Okay, we can always do this using a decoding algorithm, right? I can always, if R happens to be a code for which I have an efficient decoder, I can take R, plug it into the decoder. It will output the closest C, and then we can output the ith coordinate of C. We can always do that. But because we are only looking for local information on C, maybe it's what we would like to do is to do something better. So the question is, because we are looking for local information on C, can we do better? I mean, do we have to globally decode and then output something, or can we do something better? For instance, one of the things that you'd be tempted to do is, we know that R and C are close together, and I want the ith coordinate of C. So we could go and try and output the ith coordinate of R itself, right? But what's the issue with this? Yeah, if there's an error in the ith coordinate, then we are doomed. Right? So a locally decodable code is a code that admits algorithms of this kind, where we are going to be interested in a particular, we are going to be given a received word, a word that's close to a code word of the code, and an index into a coordinate. And the goal will be to find this coordinate with only local access to the received word. So our goal will be to not read the received word in its entirety, because then we can just globally decode, but read it at a few places, and from that try and figure out what the ith coordinate of the code word is. So let me formally define this. So C is so code C is said to be an say T comma epsilon locally decodable code. If there is an algorithm A that on input so that for every R in sigma to the n, sigma is the alphabet over which we are working, and C in capital C, and I in n, satisfies the following. There are two things that the algorithm has to satisfy. The first thing is that if the distance of R from C is small, so it's less than the distance of R from C is small, so that's less than epsilon n, then A outputs C sub I, the ith coordinate of the code word, with let's say probability 0.9. So if R is close to C, if the number of points, number of coordinates where R and C disagree is at most epsilon n, then A outputs Ci correctly with probability 0.9. And two is that A only queries at most T locations of R. Okay, so this definition is as follows. So we'll say that a code C is some T comma epsilon locally decodable. So there are two parameters, T and epsilon. Epsilon is the error parameter. T is the query complexity of the code. So T comma epsilon locally decodable, if there is some algorithm a local decoding algorithm A, such that for every R, every word R in sigma to the n, every code word C in capital C, and every coordinate I in n has the following properties. The first property is that if R and C are within an error epsilon, then A outputs the ith coordinate of C correctly with probability at least 0.9. The second property is that while in order to do this, A is not allowed to look at the entire received word R. A only has to read at most T coordinates of R. That's the local part of it. It wanted to output local information, so it's only allowed access to local, it's only allowed local access to the received word. Is the definition clear? And you should typically think of T as being much, much smaller than N. Think of T as, there are various regimes of parameters. We'll see some constructions. You could think of T as being little of N, certainly, but you could also think of T as being constant. So T is a constant independent of N, and we are looking for objects like this. Is the definition okay? Okay. Questions about the definition? All right. So one of the, this definition is only interesting if I show you that there is a locally decodable code. If there are no objects satisfying this property, that doesn't make the definition very interesting. One of the weird things about LDCs, locally decodable codes, is that, no, I is given as an input. I is a part of the input. It only has to output CI, that coordinate of the code. So a strange thing about the definition of locally decodable codes is that, a running theme in coding theory and computer science in general is that once we define an object that is of interest, often random objects happen to have those properties. This is a definition where a random code is not going to be locally decodable, a random linear code is not going to be locally decodable. In fact, the code we saw, Reed-Solomon codes, are not locally decodable with interesting parameters. So we have to define a new code, and so somehow the fact that a code is locally decodable has to be sort of built into the definition of the code itself. It's not a property we can expect in general. So let me define a code. These are called Reed-Muller codes. And this is a very natural generalization of Reed-Solomon codes. So Reed-Muller codes come with a bunch of parameters. So there are two parameters here of interest, M, which is, I'll call it the number of variables, you'll see what this means, and K, which is the total degree. We are going to be working over a finite field FQ. Q is going to, FQ is going to come, be a part of the definition. And you should think of K as being smaller than Q. So think of K as being like 0.1 Q, for instance. So just as in the Reed-Solomon definition, we thought of K as being smaller than Q. In order to get good distance, you should think of K as being smaller than Q. We'll see what the dependency on the distance is. And the Reed-Muller code with these parameters, so M, K, Q, is going to look like the Reed-Solomon code. So it's the evaluation of, so P of A1 up to AM. Let me write this slightly differently. So the code words are now going to be evaluations of M-variate polynomials over FQ with total degree D. Reed-Solomon codes for the evaluations of one-variate polynomials of degree K over FQ. These are going to be evaluations of M-variate polynomials. So you can think of a code word as follows. So this is P of A, as A ranges in FQ to the M. And P is in FQ adjoin X1 to XM, and total degree most. It's the multivariate generalization of a Reed-Solomon code. Is the definition clear? Okay, so let's study some properties of the code. This is clearly a linear code over FQ, right? Why is it a linear code? The same reason that Reed-Solomon codes for linear codes. We can take two code words, take linear combinations, we get another code word. Yeah. No, P is a multivariate polynomial. So it has to, I have to give it an M tuple. So I'm giving it an M tuple. Yeah. Good. I should have said this. Yes, A has to be randomized. So what happens if A was deterministic? So, right, I mean, let's take an example. Suppose I wanted to decode the first coordinate of the code word, and I was trying to do this for a deterministic algorithm. There was a deterministic algorithm that was going to do this. Because the algorithm is deterministic, the moment I give it these inputs, we know what locations it's going to query. And that's a small number of locations. We can always go and mess those up and make the algorithm fail. So local decoding algorithms are, they have to be randomized. Okay. And we'll see an example and you'll see where randomness is helpful. Okay, so it's a linear code. What's the dimension of the, what's the rate of the code? Yeah, I mean the size of the code is something like, so for every P of M variables and degree at most K, there is a code word. Right, so the rate of the code is M plus K choose K divided by Q to B. We are, yeah, K less than, yeah. So we are in the setting when K is less than 0.1 Q, K is less than Q. Okay. So the rate of the code is this. What is this number? What does it look like? Various regimes of parameters. So we can look at two special regimes of parameters. If M is a constant and if K is a constant. If M is a constant, let's do M is a constant. If M is a constant, what does this look like? It's, yeah, it's roughly, if M is a constant, it's like K to the M over M factorial times Q to the. And maybe, so now it looks like K to the M over M factorial. Okay, so I mean, it's a code with some rate. In the setting that we are in, we will think of K as being like a constant fraction of Q. So K to the M is like 0.1 Q to the M. So this is like 0.1 to the M divided by M factorial, etc. So rate is, as M grows, the rate decreases exponentially. Nevertheless, these are great codes, as we'll see. What about the distance of the code? Where did the distance of a Reed-Solomon code word come from, of Reed-Solomon codes come from? It came from the fact that two distinct low-degree univariates can't have too many agreements. Where should the distance of the Reed-Muller code come from? Schwarzschild lemma. So we again want to have we want to argue about the distance of the code. We have to argue that two distinct code words can't have too many agreements, right? And a generalization of the univariate statement that we saw also is true in the multivariate setting in some sense. This is called the Schwarzschild lemma. Yeah. It's approximately.
No, I mean the first.
Ah.
For example, Q equals 2, then you should have a sum. Binary.
So here, no, this is exactly. Yeah, but yeah, so we are in this setting when Q is much more than K. Yeah, so then this expression is exact. Yeah. So Schwarzschild lemma. So what does it say? It says that. Okay, so the number of zeros of a non-zero degree k m-variate polynomial in fq to the m is at most d times q to the m minus 1. Okay. Oh, there's no d. Yeah, sorry. K times q to the m minus 1. So the number of non-zeros of a degree k m-variate polynomial in fq to the m is k times q to the m minus 1. For m equals 1, this is k. This is the statement we had. But yeah, for larger m, this is the bound we have. I've written it in a way in this setting where we are over fq, etc. But the statement is more general in some sense. But this is the statement we'll be sticking with. So again, how does this imply the distance of that code? If you have two code words, so they correspond to polynomials p1 and p2, and we are looking at the distance between, let's count the agreements between p1 and p2, and the number of coordinates they agree is the same as the number of coordinates where p1 minus p2 vanishes. And p1 minus p2 is a non-zero polynomial of degree at most k m-variate, and we are trying to count the number of zeros in fq to the m. That's going to be at most k times q to the m minus 1. If you look at, so the distance of the code is q minus k times q to the m minus 1. So distance is q minus k times q to the m, q to the k minus, q to the m minus 1. If we look at the fractional distance of this, which is distance divided by the length of the code, the block length of the code, then that's going to be 1 minus k over q, which is the same as the distance we had for Reed-Solomon codes. Right? So the fractional distance of Reed-Muller codes in this setting is the same as the distance of Reed-Solomon code. So it is a generalization in some sense. Prahladh, we are running out of time now. Okay, so I'll stop here and I'll continue next time. So our plan for next time, the first thing we are going to see is a local decoding algorithm for Reed-Muller codes. We'll see two examples of this, and then we'll move on to other things. Questions? Sorry, the last bit was a bit rushed, but happy to take questions. Yeah. Yeah. Neighborhood in what way? Yes, it is interesting. You asked a yes, no question. I don't have to tell you why. I think you have to look at maximally recoverable codes. No, but it is still an interesting question in some regime of parameters. Swasik? Yeah. Locally recoverable. Yeah. Yeah, don't say that word at all. Yes, there is a distinction and it is important in some cases. This is the definition we are going to speak. Yeah. Yeah.
The issue could have been that by expanding my set of code words, I now have code words that are closer than
Yeah.
The
other thing is that you're now embedding it into a humongously long block length. So the trivial decoder is local in that way. Other questions? Okay. Okay, if not, thanks.